For any function z equal f of x, y, we define something called the Hessian matrix, which is the matrix of the second order partial derivatives, these terms here. And what we want to do is calculate the determinant of the Hessian matrix. So we will call that h of xy, and that's the determinant. We use vertical bars if you remember. And this gives us the product of the second order partials of x and y minus the product of these two. But we know that the cross partials here are exactly the same quantity. So this gives us the square of this quantity right here. Now in calculus 2, when we considered a conic section with potentially a rotation of axes because of the xy term here, we had a simple way of identifying which of the conics we had. So we considered the 4ac minus b squared. Only looking at these coefficients here, we had three possibilities. This was greater than 0, it was equal to 0, it was less than 0. Now, turns out, if this quantity was greater than 0, we knew we had an ellipse. If it equaled 0, we knew we had a parabola. If it was less than 0, we knew we had a hyperbola. And this is how we could quickly determine what the shape was before we even did anything with the rotation of axes. So now I want you to imagine that this is simply a level curve of a three-dimensional surface. Most specifically, let me replace 0 with f of xy. Now imagine we have f of xy is this conic, but now it's three-dimensional. So I want you to consider, if we look at the partial derivatives first of all. So if I said, what is fx? Then I would get 2ax plus by plus d. If I said, what's fy? We'd get, from that position right there, bx plus 2cy plus e. Now let's look at the cross partials. fxx would be simply 2a. fyy would simply be 2c. And finally, the cross partial, fxy, which would equal fyx, I either take the derivative of this one with respect to y, or this one with respect to x. In either case, I get b. So now let's look at the Hessian. If we consider the Hessian of this, or the determinant of the Hessian, I actually should say, I would get 2a, b, 2c. And we notice that the value of the Hessian is, 2a times 2c minus b squared. We get the exact same value when we take the Hessian of this three-dimensional conic as we did when we did this. So we're going to consider, how does this affect our naming of this particular shape? Now it turns out we use the Hessian to determine whether we have a maximum, a minimum, or something else when we have a three-dimensional surface. Now there are extensive lecture notes and examples that are already posted that you can view in addition to this. But for right now, let's consider these three cases. It turns out maximums and minimums can only come from this shape here. This would be inconclusive, but this is the interesting one here. Because the one that gave us a hyperbolic cross-section in 2 dimensions, turns out if we consider something like this, we've seen this shape before, our hyperbolic paraboloid, that's basically what we'd be looking at. And the idea here is I have these little within the shape. So when I'm looking at this from one point of view, I am always seeing the vertex of the parabola. I'm always seeing the highest point. But when I look at it straight on from this point of view, that looks like the lowest point. So depending on your point of view, it's either the highest or the lowest, which actually makes it neither. And we call this interesting point in space, as we've said before, a saddle point, which is the most confounding of all points, but probably the most interesting. So now again, if you go to the notes and view some of the examples, you'll see where we can take this even a little bit further.